Good evening, everyone. Yeah, thank you for coming to the talk, and thank you, Rob, for the invitation so that I can have the opportunity to give this tutorial about the solar photovoltaic technologies. So a little bit by myself. My name is Xihua. I'm in the electrical and computer engineering at the University of Alberta. In this talk, I'm going to talk about the history of solar photovoltaic technologies. So basically, the PV is a short name for photovoltaic. And then I will give you a review about the current PV devices and systems. So typically for PV devices, we call it solar cells. And after that, I'm going to give a short look at for the PV industries. So basically, the information I gathered through the internet about what happens in Germany and the United States, who are the two leading countries in the world developing photovoltaic technologies. So in the end, I will propose and talk about the new technologies in this area. So for photovoltaic, basically this term coming from this effect, we call it photovoltaic effect. So photo here means, is a Greek word. That just means light. Voltaic comes from voltage. Actually, this just means if you have light, light will introduce voltage. So that effect, we call it photovoltaic effect. So this is a pretty old effect, has been discovered more than 150 years. What happens is, if you look at this material, if you shine the light onto the material, for example, the sun, you're going to generate a voltage. If you connect both sides, top and bottom surface, you should be able to get electricity from this piece of material. So we call it photovoltaic effect. And if you further zoom in and look at its material itself, you should be able to see this. So when the light comes for this piece of material, usually we call this material semiconductor. So for this semiconductor, when you see the light, you will be able to see an electron and the positively charged particle, we call it holes. So this electron and the holes, basically they have different energy. So in this case, the light energy was converted to electrical energies. So go through the external circuit, you should be able to get electricity. So in this case, we say PV just to convert photons, that means light, into electrons, means electricity. So photovoltaic technology is a technology to convert light into electricity. So a little bit about the technology itself. If you further zoom in this area, you should be able to see this. So that just means that the electrons inside this piece of material, semiconductor, when they see the light, actually this electron will jump to a higher energy state. So we say, oh, this electron gains high energy. And when it jumps to a high energy state, it will leave empty space here. We call it a hole with positive charged particles. And when it goes through the external circuit, it went back to its ground energy state. In this case, we generate electricity. A good analogy for this will be for this little kid. It climbs up the ladder, and it looks like they see the light, and then go down through the slide. So this is more like external circuit. So in this case, this is how the photovoltaic works. So a little bit information about the history of photovoltaics. As I said, this is pretty old technology. So the first discovery of this PV effect is back to 1939. A French scientist discovered that, okay, when you have two electrodes inserted into a liquid, we call it electrolyte. Actually, for that time, it's not solid piece. It's electrolyte. It's a liquid. And you'll be able to see certain voltage produced between the two electrodes. And he discovered photovoltaic effect. So later on, almost 60 years later, first American inventor demonstrated this photovoltaic effect from a solid piece, not from silicon, all the things we know, but instead from selenium wafers. So a great contribution to the theory of photovoltaic effects actually came from this famous guy. I'm sure you all know that. That's Albert Einstein. So in 1905, Albert Einstein published a paper about photoelectric effect, basically explains how this effect happens. And for this, his explanation, basically, he won the Nobel Prize in 1921. Unfortunately, he didn't win the Nobel Prize for his famous theory about relativity. He won the Nobel Prize for his explanation about photovoltaic effect. So the practical inventions about silicon photovoltaic devices actually came in 1954. So this technology was demonstrated by 3 Americans. So this is a picture for the 3 guys. And they basically invented the first silicon PV. And at that time, actually the cost of silicon solar cell is very, very expensive. If I want to put a number here, people said it's $300 per watt. And at that time, if you look at the power generation by other method, it's 50 cents per watt. So that's kind of the time people invented this great technology, but still not competitive with other technologies. Of course, at that time, people jumped in. We know that it's very important. We can convert sunlight into electricity. Sunlight is free. You don't have to pay to get sunlight. So a lot of people actually jumped into this area. And other people also jumped into this area. At that time, another important silicon technology got developed. That is called the silicon field effect transistor. And today's modern computers, for example, the CPU memory device was developed based on silicon field effect transistors. So basically, 2 bunch of scientists jumped in. One worked on silicon PV, the other worked on silicon field effect transistor. Of course, we know 50 years later, these people working on FET field effect transistor get rich because of computers. Silicon PV still not that time. Maybe nowadays it's a good time. And later on, people always try to find applications for silicon PV because it's quite expensive, so who can afford that? So first real practical applications come from the satellite. Because if you want to send satellite into space, we are looking for the source of electricity. And the satellite can see the sun. So basically, if we use a PV cell, we should be able to get electricity from the sun. So in this case, in the 1950s, the people tried to put solar cells into satellite. For example, in 1959, in that satellite, actually it has 9,600 PV cells connected together in series and in parallel in order to power the satellite, only for the electrical part. And if you look at the size of the solar cell, it's pretty small. It's only 1 centimeter times 2 centimeters each. Of course, technology always takes time to develop. And later on, in 1964, when NASA launched another satellite, actually it has 470-watt PV array, which was the power enough to power the whole satellite. So from that time, actually, the photovoltaic was a major energy source for satellite in the space. In 1970s, the price of silicon PV got dropped because of advancement in technologies. So now it's about $20 a watt. So then people try to look at other type of applications. The good application will be, say, power navigation, warning light, and horns, and other applications in the remote areas. Usually in the remote locations, you have no access to any type of energy source, and solar cells may be a good source to power them if the price is quite low. Actually, the major commercialization effort happens in the 1970s because solar cell is low at that time. So in this case, the first demonstration of PV system for residential house and also for small-scale PV system, 3.5 kilowatt PV system, was developed in 1970s. Of course, probably you'll notice in 1980s, early 1980s, the oil price dropped a lot on the market, and because of that, the other competing technology also get very cheap. So in this case, the technology development of silicon PV got slowed. And even for that, in 1985, the University of South Wales in Australia actually breaks the technology barrier. They produced 20% efficiency for silicon solar cells, silicon PV. In 1994, the United States National Renewable Energy Lab, who is now the leading research center in the world, developed multi-junction solar cells which can exceed 30% efficiency. Of course, this type of solar cell are much more expensive compared with silicon solar cell, maybe 100 100 times more expensive compared with silicon PV. And of course, nowadays, all the satellites are using these multi-junction solar cells because for space applications, they don't care about cost. So a little bit information about myself, why I'm interested in silicon PVs. Actually, my career path changed in 2008, 2009. And you all know that this guy, President Obama, was elected in the United States. He is a lover of renewable energies. Also, he tried to push silicon PV, renewable energy, as a major energy source for the futures. And probably you don't know that this guy, called Stephen Drew, who is a Nobel Prize winner in 1997, who also was appointed as the Secretary of Energy by Obama. And I still remember in late 2017, when I go to a national conference in the United States, I actually listened to a talk given by Steve Chu, and he talked about the great future of renewable energy. Actually, from 2017, there already a big push all over the world. And inspired by that, I'm thinking, okay, I should jump into this promising field, try to use my knowledge to make contributions in technology. So basically, I moved from Boston University to University of Toronto, and I started my postdoc over there and work on solar cells from January 2009. The type of study I'm working on is called quantum dot solar cells. So quantum dot is actually a quantum material. It's very, very small. If you look at here, I use a small dot to represent these materials. Typical size about 3 to 7 nanometer. And the amazing thing for this quantum material is if you shrink the size of the material, even it's the same element, for example, lead sulfide, if I shrink the size, then it's 7 nanometer large, and its band gap, its electrical property, so that it can absorb near-infrared light. When you further shrink the size down to 3 nanometer, it can only absorb visible light. So in this case, I made a contribution, actually it's a great contribution in the scientific community, is I demonstrated the first tandem colloidal quantum solar cell use a single material, lead sulfide. So basically in this type of device, I have two types of quantum dots, integrated them together for two junction solar cells to harvest the sun energy. So this is a spectrum of solar, and this amount of energy harvested by this type of quantum dot, the red things harvested by this one. And later on, I jumped into University of Alberta, and you may ask, why come here? Of course, if you do scientific research, it doesn't matter where you are, and you can always make scientific contributions. But in terms of solar, if you look at the solar irradiance we receive in Edmonton here, actually, if you look at this map, we have more solar irradiance compared with Toronto. So basically, if you look at this color plot, this color represents, so in a year, total amount of sunlight, the energy you receive. So in Edmonton area, we have here between 1,200 to 1,300. Toronto is only between 1,000 to 1,100. So in this case, we say in Alberta area, we have more solar resources compared with Ontario. But unfortunately, if you look at the PV development in Ontario, and due to this aggressive incentive programs, the PV system there has developed better. So now I'd like to switch the gear, talk about the technology side. I'd like to give a brief review about current PV technologies and systems. So in this part, first I'm going to tell you how solar cell works. And then I'm going to cover the materials and efficiencies about regular solar cells you may see on the market or from literatures. So then I will talk about how you can construct a PV system from the fundamental very small solar cells onto large system. In the end, I want to raise the attention to talk about a particular technology called concentrator photovoltaics. So how PV cell works? So if you still remember the second slide I showed you about the semiconductors, so this is a similar plot. So when the semiconductor receives the sunlight, we call it a photon. This represents the photon energy. You're going to pump electrons from its low energy state into high energy state. So in this case, we have an electron and a host. The electron is going to transport are also transported and collected by the 2 electrodes. Of course, we're going to go through 3 steps because this is not a scientific workshop, so I don't want to go through the details about that. So in the end, you still have high energy for electrons, low energy for holes. Once it goes through external circuits, and you're going to have this voltage applied to the 2 ends of a light bulb. In this case, you're going to see electricity running through the light bulb, and you're going to heat it up, you're going to see light. So this is the idea of how PV devices work. So in terms of solar cells, of course, silicon PV is everyone know. And actually, in the development of solar cells, there are other type of materials jumped into these communities. Because in the beginning, as I showed you, in the 1950s, even 1970s, you still get $20 per watt. So people always try to propose new type of material to lower the cost of solar cells. So in the development of solar cells, people in the society divided the stage into 3 things. First, we call it first generation solar cells. It's mainly silicon solar cells because that's the first type of solar cell get developed. So in terms of silicon solar cell, it also can be categorized into 2 things. One is called the monocrystalline silicon. The other one called polycrystalline silicon. So monocrystalline silicon have the best efficiency. So the world record efficiency is close to 27%. So by the way, the theoretical maximum efficiency is 31%. So this is very close to the theoretical maximum efficiency. And for the polycrystalline silicon solar cell, the efficiency gets lowered a little bit, up to 20%. And this material, of course, are quite thick. So if you look at if you look at PV panel, it's pretty thick, but the solar cell itself actually quite thin. It's about 200 micron in thickness. So for second generation of solar cells, there are 3 types of materials. One is called amorphous silicon solar cells. The world record efficiency is about 14%, which is below compared with others. And the other one is called cadmium telluride thin film. World record efficiency is 22%. And the CIGS represent 4 elements: copper, indium, gallium, sulfide. And world record efficiency is also around 22, 23%. Amazing thing for second generation solar cell is, if you look at the thickness, it's really thin. It's 1 to 2 micron compared with 200 micron. So there's a big change here, because when the material are very thick, like 200 micron, it's pretty fragile. If you bend it, it will break. So for silicon PV, you cannot bend it. But for second generation solar cells, it's very thin, 1 to 2 microns. So even for the same type of material, when you thinner that down to micron scale, if you bend it, it's not that fragile. Actually, you can put it onto flexible substrate, and you can bend it. So that's an amazing thing for second generation solar cells. Of course, both first generation and second generation has been commercialized. If you look at the manufacturers, you should be able to find companies manufacture all these type of solar cells. So the third generation solar cells, we call it emerging PV technologies. That's the major things people develop in academic institute or startup companies. And efficiency-wise, it's not that good. The reason is for the silicon, and this has been developed for more than 30, 50 years. All this new technology, only 10, 20 years. We still need time to catch up. But efficiency-wise, it's not that bad. If you look at organic solar cell, dye-synthesized solar cell, colloidal quantum dot solar cell, the one I'm working on, they all have efficiency about 10%. And recently, amazing material called perovskite solar cell have the efficiency close to 23%. Very good. So now let's just look at individual type of solar cells. And for silicon solar cells, so this is the way how to manufacture that. If you look at all the manufacturers, vendors of silicon solar cell, they all get manufactured with similar approach. So first thing is you're going to get material called silicon dioxide. But you cannot use the sand because sand is very dirty. You may have 70% of silicon dioxide, 30% of other impurities. So in this case, you want to use, we call it ultra-pure sand. And start from that, you're going to go through a process high temperature reduction process to get 98% pure. We call it metallurgical grade silicon, MGS. That's this one. And then you're going to go through another purification process, the distillation process. If you've ever been to a manufacturer plant, try to produce polymer, etc., you will see the big tower, distillation tower. So basically, silicon solar cell goes through the same process. They also have a distillation tower to do it. Probably you don't know it. And after that, you have very high quality, we call it electronic grade silicon, EGS, that's this one. And then go through this process to get crystalline silicon and manufacture cell and put a lot of cells together. You should be able to get, we call it module or panel. So that's the way to manufacture solar cells. For the second generation of solar cell, called the thin film solar cells, the way to manufacture that is a bit different. Because now, the way it works is you can use flexible substrate. Or maybe you still stick with rigid substrate. So for the flexible substrate, what you do is it's only 1 to 2 micron thickness for the light absorbing material, amorphous silicon, cadmium telluride. So usually people use the equipment called physical vapor deposition to just deposit this material onto a substrate. And after that, they coat a conductive electrode on top. You should have the device. A famous example will be this. Probably you have this type of calculator more than 20, 25 years ago. If you look at this piece, that's a silicon solar cell, but not crystalline silicon. It's amorphous silicon solar cell. The efficiency is pretty low. As I showed you before, world record efficiency is only 14%. Probably this piece only have 10% or 8%. But we don't care about the efficiency. As long as we leave it under the room light, we should be able to power these calculators. And the amazing thing, as I said, second generation, you can put it on flexible substrate. So if you look at this guy, kind of sitting at nowhere in the Earth, and he has satellite cell phones, and chart that with flexible solar cells. So that could be a neat applications for second generation solar cells. And now I'd like to show you how to construct a huge PV system from basic solar cells. Because if you look at the solar cells, from the fundamental physics point of view, the voltage you can generate is only 0.6 volt, very small. And the current, if you look at that, is DC current. DC current means the flow direction for current is always follow one direction. But if you look at the electricity we're using these days, it's called AC, basically alternating electricities for forward and backward directions. And also voltage is really high, 110 volts for North America and 220 volts for Asia and Europe. So how to do that? And pretty simple, actually. So the way people work is first you have a small solar cell, and then you assemble small solar cell into a big module like this with multiple of them together. If you connect them in series, you're going to increase the voltage. If you connect them in parallel, you're going to increase current. So in the end, you put multiple modules together, you're going to get a panel. And if you look at the data sheet here, actually this is from SunPower. SunPower is a solar company in California. They produce the world's most efficient solar panels. And if you look at the cell efficiency, it's really high, 22%, 22.5%. This is not efficiency you make in academic lab. This is the efficiency you can find from their solar module, solar panels. And the panel efficiency is a bit lower, 20%, still very high. And if you have that, it's still a DC voltage. And maybe it's quite high, up to, say, 100 volt, or electricity is very high, but still DC. How to get DC from DC to AC? You have to go through the whole stage. So now I'm going to show you two types of PV systems. So typically in Alberta, we have this type of PV system. So the first one is called the standalone system. So if you have the PV panel receive the sunlight, you produce the DC voltage. And usually you use that to directly charge the batteries. Because there are a lot of batteries, we call it battery bank. So once you charge the battery bank, you can use this to provide electricity for other type of equipment in your house. For example, in remote locations, you probably prefer this type of PV systems. So for most of the case, people use this type of system. So you have to tie the electricity generated from PV panels onto the grid. We call it electrical grid. So the way it works is first you have to convert DC into AC. So the major electronic equipment to do that, we call it inverter. So if you go through some house with PV panels on sidewall, you may see something like that. That's the inverters. Of course, after the electricity passing through the inverters, you're going to have 110 volts AC current, and then you can directly connect that into grid. Sure. And of course, in the middle between inverters and the grid, you can either insert a battery bank or not. It's really up to the applications. So the last technology I want to brought in is called concentrating photovoltaics. If you remember, when I talk about the history of solar cells, in the end, I showed that for the multi-junction solar cell, the efficiency is more than 30%. That's the dominant solar cell people have on the satellite nowadays because it's really expensive, but also very efficient. So you may ask the question, how can we use that kind of efficient solar cell for the regular applications down to the Earth? There are applications for that. So this is the technology people propose. So basically, because the solar cell itself very efficient, also very expensive, so they are going to have the solar cell, this small, very small, integrated into a big system. All these are very cheap mirrors and lens. So in this case, we say you're going to combine cheap optics with expensive but high efficiency multi-junction solar cells. Maybe the ratio is 100:1. And in this case, you convert the sunlight onto small area of solar cell. So the solar cell cost is high, but in terms of the whole system, it's not that high. But a major drawback for this is actually the location of the sun is always changing during daytime, start from east to west. So you need a tracking system to track the location of the sun so that you can focus the sunlight onto the small chips. So in this case, that's why you haven't seen this type of concentrating photovoltaics in residential house or even commercial house. People only have this type of setup in the power plant. We call it solar farm. Because only in solar farm, you can put the heavy, very big tracking system for these designs. So now I'd like to talk about the PV industries, the research basically I found on the website about the production and the price trend for PV devices. So as an academic researcher, actually what I care about, what people care about, probably is not the payback for your investment, for your money, actually rather than the payback of energy. Because in order to produce solar cells, always going to consume certain energy. If this device, solar cell, we typically know it's going to work at least 25 to 30 years. So in this lifetime, you're also going to produce energy. If this produced energy is less than energy used to produce solar cells, and then probably it's meaningless to do this type of work. I think the good thing is energy payback time is not bad. And if you look at this plot, this is done by Fraunhofer Institute in Germany. As I said before, it's a leading country in the photovoltaic technologies. They did this kind of studies. They found that various type of solar cell technologies and in Germany. So if you look at the global irradiance, it's 1,000. And if you still remember the plot I showed you, in Edmonton, we have the irradiance bigger than this number. We have more than 1,200. Actually, energy payback time in Edmonton is better than this plot. Of course, depends on different technologies like silicon and also this amorphous silicon, polysilicon, cadmium telluride, CIGS. Although the efficiency-wise, all these technologies are pretty close, from 16 to 20%, but the energy involved in production are a bit different, so that's why energy payback time is different. Of course, if you look at this, single crystal silicon is not that good, although it gives the best efficiency energy payback time is a bit more than 3 years. And the amazing thing is cadmium telluride. Unfortunately, there's only one company in the world manufacture cadmium telluride solar cell. The company is also in California. The name is First Solar. I did find, say, 5-6 years ago, GE, General Electric in the United States, tried to jump into these industries. But last year, they say they're going to give up and just buy stock from First Solar. Probably there are still some technical barriers. So in this case, technology development is not as simple as we thought. So some quick facts for the PV industries. If you look at the market, because this is research done by Germany, so in this case, they listed what happened in Germany, what happened in European Union, EU, what happened worldwide. So for the PV market, actually, of course, it's a huge market now. And this is for every year in 2016. And this is the cumulative installation. So basically, you added up all the installed PV panels from 1950s up to now. Okay. And also, if you look at the worldwide, the share of productions, actually most of the share is by crystalline silicons. 90% of PV panels produced is by silicons. And other type of technologies not as good as silicon. They still need time to catch up because, as I said, amorphous silicon, the efficiency is a bit slow, a bit small. It's only 14%. Cadmium telluride, only one company do that. CIGS, a few companies doing it, but if you consider silicon PV, hundreds of companies are manufacturing that type of solar cells. And this is a plot, actually two plots, basically shows you very similar trend for the global PV production worldwide and as a function of different years. Those sudden shoot up actually happened in year 2008, 2009. That's the time we have the big push. So globally, not just the United States, but globally from Asia, from Europe, and all countries, they say, okay, we are going to invest in renewable energies. Photovoltaic is part of that renewable energies. So that's why you see a big push in the production of solar cells. And you may see that actually this line represents the production of PV panels in China and Taiwan. And you may wonder why in China and Taiwan at that time there's a suddenly shoot up, not United States or Europe. I think probably there's some little story over there. In China, actually in year 2005, 2006, there are already a few solar companies, and they made a lot of money in year 2017, 2018, because only a few solar companies in the world can manufacture solar panels. And at that time, I think in year 2007, the richest people in China actually is the owner of company manufacture solar panels. Inspired by that, and then different locations in China, they say, oh, this is a great opportunity. They want to jump in. So suddenly there's a jump in the manufacturing of solar panels. And of course, in the installation of solar panels, not just China, but also other type of area in Asia, for example, Japan, and also in Europe, in North America, in US, and also here in Canada, in Ontario, the installation of PV panels get increased a lot. So the annual growth, I would say, probably more than 50%. And also, if you look at the price for PV itself, actually, unexpectedly, the price of PV cells dropped a lot. When I jump into this area in year 2008, 2009, I go to academic conference. A lot of people want to do academic study, the research onto solar panels. The big argument we have at that time is, if you look at the price of PV panel, it's pretty expensive. Even for silicon, it's very expensive. If you look at the point, year 2008, this is in Germany, it's about $5. Okay? In that $5, this is the cost of hosting, the whole system. Within that $5, maybe $4 is for solar panels. Okay? And then people say, yeah, $4 is too expensive. If we can reduce that to 0.4, that will be great. And then you will see a lot of guys invest different type of new materials for silicon solar cells. Unfortunately, nowadays, we already have that value, $0.4, $0.5 per watt for silicon PV. And of course, later on, you're going to see for the emerging PV technologies I presented today, I'm going to show you different type of solar energy the silicon PV cannot do. And this investigations was done by United States, so US. They did the investment on different type of PV systems, cost-wise, how it looks like. Of course, if you look at here, this means residential PV. That means the photovoltaic panels, PV panels, installed on a single detached house. Commercial PV means if you have a big building, have the PV panels installed, of course, the energy generation will be more, so up to 100, 200 kilowatt. And the utility scale means now you're going to really have a power plant, solar farm. In this case, energy generation in the order of 100 megawatt. And if you look at the cost, of course, if you have larger assembling of solar panels, the cost get dropped. So that's why from residential PV down to utility scale, the price are a bit different. So for 2017, residential PV, the whole system, if you convert it to watt, dollar per watt, it's about $2.8 US dollar. And for utility scale, it's only 1.03, 1.1. So a bit different. And if you look at what's the difference, in terms of solar panels itself, that's the yellow part. And there's not much difference because the price is bit cheap, 0.4. And actually, the most cost actually coming from this. We call it the soft cost, which includes land acquisition, sales tax, overhead, and the net profit. So definitely the PV industry, I know they are working on some of this, try to reduce the cost for the whole PV systems. And in the end, I'd like to show you the evolution of PV module efficiencies. And if you look at how the module efficiency works up to today, this is the only scientific report I found about the silicon modules. So I like to show that for what happens before year 2005. After year 2005, basically we can get a sense of efficiency from this energy payback time. Okay. So if you look at this plot, basically it shows you several stages. Of course, in the first time, people invented silicon solar cells, efficiency is pretty low, 2%. And got developed for quite a amount of time, up to 1970s, the efficiency jumped up. The reason is at that time, the cost of silicon PV reduced to $20 per watt. Also at that time, the oil price increased a lot worldwide. So a lot of research going on for that area. That's why the efficiency is going up. And after that, in the 1980s, because the oil price drops again, so there are less research into PV solar cells. So the efficiency kind of still slowly increased. So beyond this point, recently, if you look at energy payback time, because the energy used to produce these silicon panels doesn't change much. So if energy payback time gets improved, a major contribution actually is coming from the increase into the efficiency of solar modules. So energy payback time did decrease a lot, so that means efficiency increased a lot nowadays. If you look at what is the best PV efficiency for the modules, so this plot shows you for different type of companies and different type of solar technologies with different materials. So what's the best module efficiency? So this one is from SunPower. As I said, it manufactures a single crystalline silicon with a module efficiency more than 20%. Actually, in this plot, they have 21%. And if this is a polycrystalline silicon, that's this plot, the efficiency is still about 16%. If it's a thin film, if it's first solar, cadmium telluride, it's close to 16%. If it's the other company called Solar Frontier, it manufactures CIGS solar cell, close to 14%. amorphous solar cell, as I said, lab efficiency is 14, the model efficiency below 10. So basically, no one is going to purchase amorphous silicon solar cell. Probably you just use that for some application to power your cell phones or for the calculators. And hopefully in 20 years, in next 20 years, we're going to see new type of solar cell jumps in and pop up on this plot. So in the end, I'd like to talk about the futures, the development of solar technologies for the future. As I said, when I first jumped into the solar technology, a very good excuse for people jumping into this technology, the argument is the solar panel are so expensive. It's $4, $5 per watt for silicon PV. And if we make it $0.4 per watt, we are going to win. Unfortunately, silicon PV already done that. And then now in academic research, people are going to work on something else so that silicon PV can never do. Okay. So in this section, still I'm going to first talk about emerging PV technology. So kind of summarize what people do in the past 10 years, try to compete with silicon PV, and then I'm going to talk about two new type of technology silicon PV cannot do. So this plot, published by National Renewable Energy Lab, they kind of summarize all the world record efficiency for various type of solar cell technologies. All these green ones are second generation solar cells, thin film solar cells. All these orange ones are emerging PV technologies. Basically, you see here, for emerging PV technology, it goes probably 10 years for the efficiency climb up. Actually, I contributed to these 2 points in the, I think, 6, 7 years ago. And amazingly, you're going to see one plot here, this type of solar cell, which is called a perovskite solar cell. So for the perovskite solar cell, in the past 10 years, the efficiency jumped up to 22.7%. Now it's compatible with other type of thin film solar cells. It's really amazing. And if you look at this type of solar cell, it also has other type of advantages. For example, for the thin film solar cell, when I talk about that, I say people use the physical vapor deposition to manufacture the device. Actually, for perovskite solar cell, in research, people use solution process. Solution process means you can process something like printing papers. For example, this is the way people propose to manufacture perovskite solar cell. There are already been several startup companies in the world try to commercialize these technologies. And if you look at the thickness of perovskite solar cell, it's so thin. This is 200 nanometer. So 1,000 nanometer is 1 micron. So the whole thickness is less than 1 micron. So it's really thin. Of course, you can put this onto flexible substrate. And also, you can manufacture that, use solution processing. Usually, people will say, oh, this row-to-row printing compatible process. And this is a demonstration. People use a model flight, power that with perovskite solar cell. Of course, this technology has only been there for less than 10 years because the first efficient perovskite solar cell with efficiency about 3.9 was demonstrated in year 2009. So it's just 9 years. And hopefully in the next 5 to 10 years, we're going to see perovskite solar cell get commercialized, try to compete with silicons. Another amazing thing I forgot to mention is here I listed different colors for the bottles. The reason is for these perovskite materials, actually you can tune the color of this material. You can exchange lead into other non-toxic element. You can also exchange the iodide into bromide or chlorine. In this case, you can tune, we call it band gap of the material, so that you can see different colors for the perovskite. So if you need certain application, you don't care about efficiency, you care about the color of the cell itself. Maybe for certain application, I have no idea, and you can use this with different colors. But still, this is some technology you still want to compete with silicon PV. As I said, silicon PV can still decrease their price and kick you out of the market. So in the end, as I said, I'm going to talk about two new technologies which silicon PV can never do. So the first one is a new concept. People call it artificial photosynthesis. So photosynthesis actually is a chemical process happened in nature. If you have any plant, when it sees the light, actually it's going to absorb carbon dioxide, also water. There are going to be some chemical reaction happen, convert carbon dioxide and water together into oxygen. So this process, we call it photosynthesis. Inspired by this natural process, scientists say, okay, let's do something very similar. We call it artificial photosynthesis. There are two things they're going to chase. So one is we're going to convert water into hydrogen and oxygen. So it's also a chemical process. The other one is we're going to capture carbon dioxide, because we all know carbon dioxide is not good. So why don't we capture that and convert that into valuable products like methane, carbon monoxide, etc., any kind of hydrocarbons. So basically, this is the idea. And for example, if you want to get hydrogen from water, then you can burn the hydrogen. It's a really clean fuel. If you burn hydrogen, you should be able to get water. But there are still some safety issues. If you don't do things carefully, you may get explosion of hydrogen. So how this works scientifically? So there are some smart people in the community. Basically, they propose some idea like this. They're still going to use solar cells. So this is a solar cell. Typically, for the solar cell, you're going to see the sunlight generate voltage. At this time, they're going to put some particles, we call it catalyst, on both two electrodes of the solar cells. And for one electrode, they're going to generate hydrogen. The other electrode generate oxygen. So this process, people call it photoelectrochemical or photocatalytic reactions. So basically, this is for get hydrogen, so they call it water splitting. And of course, this is the thing we can do. Nowadays, people already have this system quite efficient to achieve the conversion efficiency above 10%. But actually, what people really want to do is something like this. They don't want this wire, because if you have the wire, system gets very complicated. So why don't we get rid of the wire, directly coat the two surfaces of the solar panels to have these freestanding systems? Of course, it looks simple, but scientifically, there are a lot of challenges over there. For a system like this, it's only 5% nowadays. But still, it's not enough, because we still use solar panel. It's pretty big. And some people in the world, they think, can we do something more? For example, we can have some small particles, could be nanoparticles, could be big, microns or millimeters, and we just drop these particles into water, and then have the sunlight shine on that. Instantaneous, we're going to generate hydrogen and water. There's no solar panel involved. That's a good dream. People are still working on that. And the idea is we're going to have some type of semiconductors, amazing semiconductor, as the particles, and directly coat two types of catalysts onto these nanoparticles. One generate oxygen, and one generate hydrogen. Exactly the same idea, but people still working on that. This is just, say, not a dream, but very, very challenging in scientific research. So a lot of people kind of working on this type of ideas. So in terms of carbon dioxide reductions, the setup is very similar to water splittings. People still have two electrodes. They coat a different type of photocatalyst on two electrodes. So in this case, on one electrode, we are going to convert this small molecule, is carbon dioxide, into other valuable hydrocarbons, okay, like carbon monoxide and HCOH, or this one CH4 called methane. And the other electrode, basically, you're going to generate hydrogens. Hydrogen diffuse through and provide hydrogen for chemical reactions. Of course, people already have this type of freestanding setup for CO2 reductions. I think for this scientific study, most important thing, of course, increase the efficiency to 20%, try to compete with silicon. Of course, you want this dream setup, just nanoparticles or particles drop into water. You're going to get free energies. So the other new development I propose Actually, I'm working on this type of setup. It's called luminescent solar concentrators. So for luminescent solar concentrator, it's coming from the idea of concentrating photovoltaics. Because for concentrating photovoltaics, we know that for this setup, we have to track the location of the sun. And because we need to do that, in this case, we need these big, heavy tracking systems. So it's not possible to integrate that into residential or commercial buildings. And instead, people propose this type of setup. They say, let's have some sort of film. For this film, we call it luminescent solar concentrator. The way it works is, for this film, when it receives the sunlight, it can use these particles, could be organic, could be inorganic materials. And when it receives the sunlight, and it can emit light with different wavelengths, and then guide this light to the side of the film. For the side of the film, of course, you can put regular silicon solar cells and collect this amount of energy. In this case, you don't need to track the location of the sun, because at any location of the sun, you should be able to see the light. So in this case, you put it for the windows of the buildings or the parking carriage. Even for the north side of the building, where you didn't see the direct incident of sunlight, it's also the diffuse sunlight. You can still use this setup. So this is a really good idea, which silicon solar cell cannot do. So in my academic research, in my lab, basically we just explore the similar things. And this is the setup we have, the concept. So we put a quantum dot, because as I mentioned before, I'm working on quantum dot. So I put a quantum dot into this luminescent solar concentrator. Why I put a quantum dot over there? The reason is, traditionally, this technology has been developed for 20, 30 years. Previously, people used material called organic materials. For organic material, this triangle represents its absorptions, and this dot represents its emissions. If you look at here, there's a great overlap between absorption and emissions. As I said, when the film receives sunlight, it's going to emit like this. And if there's a big overlap, and then emitted light gets absorbed again, which is not good. And another factor is, if you look at organic materials, the absorption is more like a band. So it only absorbs start from probably 470s. But if you look at the sunlight spectrum, it starts from 350s. You're going to miss a lot of solar energies. In this case, we propose to use quantum dot. Because if you look at, this is absorption for quantum dot. It's pretty above, and down to 350, we can absorb a lot of sunlight. Of course, there's still overlap between absorption and emission. But if you look at the portion of the overlap compared with the portion of absorptions, this overlap is much smaller compared with organic materials. In this case, you should be able to gain higher efficiency compared with organic materials used in luminescent solar concentrators. So in the end, I'd like to conclude my talk with this slide. So probably you see this anywhere in Edmonton, and you probably, some of you have the chance to see a solar farm like this. This basically represents nowadays technology, and we know that global energy consumption rate nowadays in the order of tens of terawatt. So in year 2002, this is 13.5 terawatt. People predicted in 2050, this number is expected to be 30 terawatt. So what we can do with solar? And if you look at the solar energy, actually we have a bunch of free energies from the sun. So for solar energy, for the energy received at the surface of this Earth, it's 1.5 times 10 to the 5th terawatt. And that means we can convert 0.05% of Earth's surface. Of course, there are only 30% of Earth's surface are land, and the majority of them probably not good to put solar cell. And even 0.05% with 20% efficiency module, which somehow already have, we should be able to have 15 terawatt. So that means just for solar energy itself, it should be enough to power half of these energies. Of course, if we do that, we probably have to put solar panels in a lot of places. And if you look at in the future, what the future looks like, even on the farm, we have the animals, they have to live with the solar panels. And of course, this is artificial leaves, and this is the idea people propose, artificial synthesis, and even for the solar concentrators, you put it onto the buildings. So that may be the future in 20, 30 years. Okay, so this is the end of my talk. Thank you.
Thanks, Dr. Wang. I see you're close enough, getting up to, you were talking about the sun powers are up to a 24% efficiency in that. We've been through some of the different seminars as a dealer and, or installer in that the new LG neons are pushing from 24 to 26% efficiencies. The bifacials, so that's a new product that's being promoted since the build of the Londonderry Mall with the car parks there and that, so that it shows with the sunlight coming down through the modules and then back up again, facing back up, and increasing the efficiency of the modules. Have you done some research on that?
Yeah, I think that's a good question. Apparently, I didn't notice this great achievement from LG, as you mentioned. They're quite ambitious. If they claim they already have 26% module, I'm not sure whether they really have that, because according to the studies, it's not my study, it's renowned researchers in the world. If you look at this efficiency chart, so monochrome silicon, world record efficiency is 26.6%. This is produced by the university lab. The size of the solar cell is in the order of centimeter square. That's why it's so high. And if you talk about the module cells, big piece, usually they have 24% or lower. And if LG did claim they have 20%, 26%, I would say, wow, that's great. But myself, frankly speaking, I don't believe it.
You mentioned solar irradiance in Edmonton is about 1,200. Yeah, this is map, and 1,200 kilowatts hour per square meter per year. So it's average year, right?
Yes.
So my question is, what is solar collector or solar panel tilt angle? Is for horizontal or for at tilt angle of latitude of Edmonton? What is the tilt angle?
Yeah, I think in order to install solar panels, you always have to install solar panels for certain angles, because at different location of the Earth, you have different angles to receive the sunlight. And for these numbers, basically, people really considered that. So this represents, in the best scenario, best case, the amount of sunlight. If you install the solar panel in the right angle, this amount of solar energy from the sun you can harvest. In terms of the exact number, sorry, I don't remember that, but definitely you should be able to Google and find that number for Edmonton.
So it's an optimum tilt angle.
Yes, you have to install solar panel at optimum angle.
Okay.
Has there been any analysis done for energy to also dispose of the product at the end of life? So the total energy consumption of that product from cradle to grave.
Yes.
Has there been a comparison done for that? And also, has there been any models or anything done to compare the different, or look at the different types of cells for total environmental impact? So that it goes from everything from mining the product to disposal of the product at the end of life.
Yeah, thank you for the question. I think that's really good questions. And when I look at the published research about this PV works, I only find people doing research about the energy payback. I haven't seen anyone doing this research on how much energy you need to dispose that. Maybe they're already being research done. Unfortunately, I didn't find it. I think it's a good, very important thing, because after solar cell has been manufactured and has been installed, after 25, 30 years, when it's not working, or I shouldn't say it's not working, because maybe you still have efficiency, not as efficiency as before, you have to recycle that. But I think the good question is, if you look at the whole industry, the big booming happens actually from year 2008 here. We are still far away from the 25, 30-year lifetime. Probably at this stage, not many people actually realize these important problems. Actually, not many companies actually has been existed for 25 years into this industry. So definitely, I think it is very important to do this kind of research, to really invest how to recycle the PV panels, how to correctly dispose that, and also how the environmental impact for different type of technologies.
It takes this silicon material to produce these cells, right?
Yes.
Is there a resource problem at some point of time to produce all this massive amount of solar panels? Is this an endless resource? I don't think it is. Can you talk a little bit about it?
Sure. And of course, if we know we need silicon in order to produce silicon solar cells, actually silicon is the Earth's abundant material, probably top 5 abundant materials in the world. So people never worry about how to get silicon. Silicon kind of everywhere, from silicon dioxide, from the sun. So in this case, people never worry about that. And in terms of price-wise, I did see, I think before 2007, the price of silicon itself, this EGS silicon is quite expensive, up to $200 per kilogram. Nowadays, it's really cheap. It's only $20 per kilogram. I think probably industry-wise, because this is, you'll see silicon everywhere, so people never worry about that.
In my understanding, the reason that silicon, both polycrystalline and monocrystalline, have dominated the marketplace for many years is that not only does it have reasonable efficiency, but it also is incredibly durable. Looking at 40 and 50 years lifetimes. And also its degradation rate is fairly low, less than 0.5% per year. So these third generation technologies that are coming along, how do they look in terms of duration and degradation rate?
Okay, thanks, Rob. It's a good question. For the emerging PV technology, as I showed here, if you look at all this technology, some of them probably show up in the previous 15 years. Some of them probably show up in the previous 8 years. Some of them probably previously 9 years, 7 years. So it's still probably too early to determine what's the lifetime for these materials. And for research-wise, the whole research effort, I would say more than 90% of the effort people spend in the society is try to clamp up the efficiencies. Yeah. Because the first thing, if you have a new material, try to compete with silicon, you have to demonstrate the efficiency-wise is as efficient as silicon, more than 20%. And then you have to demonstrate material-wise, you should be able to have this material everywhere, and it's very cheap to manufacture that. Of course, lifetime is very important. Probably you need at least 25, 30 years for the lifetime. So currently for this emerging PV technology, on the module side, there are several startup companies are working on that. Unfortunately, they are not good. As I said, this is relatively new technology happened in the past 10, 20 years. And the efficiency, the lifetime probably only a few years. Compared with silicon, as you said, 40, 50 years. Not that good. But I wouldn't be pessimistic for this technology. The reason is silicon PV got invented in 1950s. So it's more than 60 years. So they still have time for this new technology to get improved.
So what kind of degradation rates are you seeing with them?
I think for organic solar cell has been invested for more than 20 years. People see that the degradation is about maybe 1% per year. Drop from 7% device to 3% device in 3-4 years.
Solar cells are now being combined in various types of materials, such as the Tesla roof tiles, clay tiles, and ceramic tiles, and you know how that. I wonder if you could tell us anything about how that's working and how that's affecting the panels. And it seems to me that we're still building buildings without solar panels, which is just criminal in Edmonton and everywhere. You know, these buildings are going to last for 100 years, and we want to put solar panels in them. But, you know, how can we embed those panels in other materials, and how does that work?
Yeah, thank you for the good questions. Actually, although the question is not people care about in the academics, I do look at various news about that. I think Musk is a genius. So basically, he kind of tried to combine silicon PV with particular applications, as you said, on the roof. In this case, try to promote the silicon PV technologies. Because if we look at the cost of silicon PV, it's still not competitive with other type of power generation resources. But if you do propose some very unique applications, try to take advantage of silicon PV, maybe that's a very good angle, try to enter the market, try to promote these whole things. I really like that kind of applications. But still take time for us to see how these things get developed.
With the advancements in the demand, large rise in PV systems that we have for residential, commercial, could you maybe shed some light on what is being done for firefighting suppression requirements and ventilation, for safety with string arrays and DC systems, where you may not be able to, if the grid goes down, you'll still have a large voltage there, and as well as ventilation issues, just to protect our firefighters.
So there's been quite a bit of alterations to the electrical code to address some of the issues there. In terms of rapid shutdown requirements, whereby the fire department can very rapidly shut down the production of the array when they reach a site. The whole thing is moving toward ultimately module level shutdown, so each module will actually shut down in that case. So we also have ground fault interrupters that are code required to address that. So there is a lot of research going into that, and the electrical code is slowly making some changes in that regard.
Being an instructor and installer in that, we've talked with some of the fire departments and stuff like that, and what we found out, like a couple weeks ago, there was a big meeting with some of the department, the guys, and as to the answer to your question, a lot of the arrays and everything else are on one side, the south-facing side. When we were told by the firefighters when they come out, they'll just not go on that side, they'll go on the other side, on the north side, and open up their holes where there is no array, kind of thing, where there is no problem with that.
With all the new installs that are coming and upcoming trends, there's a lot of information on firefighter engineering magazines as well as websites. So there's actually online courses that are free that we're doing as departments that kind of educate the firefighters on the ground that have no idea about it. But even though they are shut down, they still contain power sources. So if we're to impact them with tools or water sources, there is a serious potential for injury. So it's just kind of the beginning stages of the training. And I think what I'm finding is as the installs become more popular and more frequent, there'll be a lot more safety in place. But for now, that's all that we're seeing.
I might add that there's quite a bit of discussion among fire departments regarding this whole issue of ventilating buildings. So a traditional procedure is if there's a fire on a building, the fire department ventilates the building by cutting a hole in the roof to allow it to ventilate. And so the big question is, how can they do that if it's covered with photovoltaic modules? Well, is happening with some of those discussions is some of the fire departments, I think this is the case in Calgary, are basically saying that they don't vent residential buildings anymore because the glue lamps and such like that go up in flames so fast that they can't really trust getting up on the roof. So for them, it's not a big issue in terms of needing to ventilate on the roof space. Other fire departments have a different view on that, so it's kind of an ongoing discussion, really.
The rapid shutdown for both optimizers and for microinverters, pretty much the fire department is there, and there's a photovoltaic. They can pull the meter, and the entire system's dead, so no issue. So that's that. But my main question was, I'd heard a lot about graphene-based and perhaps absorbing infrared, that it could be put on the outside of windows and then not interfere with the light. Have you heard anything about developments into that?
Yeah, I think it's a good question. Scientifically, there are a lot of exciting news happened for the graphene and other type of things. I want to raise this important point. Actually, for silicon solar cell, the silicon has a band gap of 1.1 eV. 1.1 EV is equivalent to a wavelength about 1100 nanometer, which is already in the infrared regions. So silicon already harvests a great amount of infrared energies. So maybe there are other materials have better efficiency, but really something actually I haven't had a chance to cover here is how to predict the theoretical maximum efficiency for solar cells. In order to predict the maximum efficiency for solar cells, we have to look at this plot, how solar cell works. So if you look at this plot, when the sun energy comes in, actually the sun has different wavelengths, different colors. That means they have a lot of photons with different energies. If the photon have energy smaller than this, we call band gap. In this case, that means this material looks like transparent for this type of photons. For example, if the sun has energy about, this photon has energy about 0.5 eV, it won't be able to be captured by silicon solar cells. And of course, if the energy is bigger than the 1.1 eV, it's 1.7 eV, for that case, when the energy gets captured by this material, and because this material won't be able to distinguish between photons with different energies. They always pump electrons from ground state up to these energy levels. So in this case, the energy beyond 1.1 eV will be wasted. So in this case, in order to search the best material with the best band gap for solar energies, there are always certain range. And if you ask me what's the range of that, I think this table basically shows you the ideas. If you look at here, 1.1 EV, 1.5 EV, and all this kind of have similar values. Actually, for the best or the efficient solar cell, it should have the band gap between 1.1 to 1.5. So if below that, even if you harvest more infrared energies, because the voltage you produce actually is lower. So in the end, it turns out the total efficiency you get will be lowered. So that's why silicon solar cell, other type of technology, always stay within that energy levels, between 1.1 to 1.5.
I guess I think the point behind the research that I had seen was the fact that you could easily produce it and it could be put on any surface, and for the fact that with infrared you're also leaking a lot of infrared out of buildings, that even though it's low efficiency, but because it's everywhere, that you could potentially still capture a lot of energy.
Yes, thank you. I think that's a good idea. It's very similar to the Tesla's solar city. It looks like we try to use different type of technology, try that for different applications. Hopefully, as you said, some infrared portion, of course, it's not going to give you the best efficiency solar cell, but maybe that amount of energy could also be useful if you don't care about the cost.
And does ambient temperature have much of an impact on efficiency of the panels at all?
Yes. Temperature did have an impact on the efficiencies. When people report all these efficiencies, you have to do the measurement at, I think, 25 degrees. And if you do the measurement at different degrees, the efficiency is different. Usually at lower temperature, the efficiency is higher, but not much difference. It's not like maybe at 0 degree, the efficiency can improve 1%, something like that. There are some impact, but not big.
So of the 4 technologies that are being researched that are third-generation solar cells, which one of them do you think is the most likely to reach the marketplace fastest?
Yes, I think if you look at these numbers, of course, the perovskite will be the candidate because, as I said, within 9 years, the efficiency climbed up from 3.9 up to 22.7, even comparable with second-generation solar cells. So if I want to bet which technology has the best chance, I would put it on the perovskite solar cells.
Which type here has the highest theoretical efficiency?
I think the maximum efficiency is really related to the band gap of the materials. And if the maximum efficiency for single junction solar cell is 33%, the material is called gallium arsenide. That's also the material people use to build multi-junction solar cell and send it to the space. So that's the type of device. In terms of silicon solar cell, because the band gap is 1.1 eV, so the theoretical maximum efficiency is 31%.
Is there a lot of research going on about short-term storage of power, something like capacitors, so that we're not looking at all these lead-acid batteries and the other things that die so quickly in our systems?
Yeah, thank you for the question. I think you did get the point. And currently, in addition to the efficiency and the price, another, say, hold point for the technology basically is how it's going to store that. Because usually you only generate electricity in the daytime, especially 12 to 3 o'clock. And if you look at what's the time people try to use electricity, that's after they go home, which already been dark. And definitely you need to store the energy. So currently, for academic research, there are tons of research over there. If you look at the research society for that area, it's even larger than the research society for solar cell itself. It's called energy storage for new type of materials for energy storage rather than lead materials, as you said. Currently, the most promising is the energy people use for your laptop computers, the lithium energy, lithium ions and other type of energy. That's the stuff people are working on. So they have a bigger community than photovoltaics.
So you mentioned when you were talking about quantum dots in that application, I was kind of envisioning that these would get placed into windows because they're transparent. But you were also talking about luminescent solar concentrations just before that. Was there a connection between the two, and I just missed it in your presentation?
If we look at the technology, and this setup films with a quantum dot other material embedded in, we call this setup luminescent solar concentrator. It's just a name people come up with to describe this technology. So in order to make sure this technology works, you need a certain material inside to absorb sunlight and also emit light at longer wavelengths. So quantum dot is this kind of material to absorb sunlight and also emit at longer wavelengths. Actually, it's not truly transparent. It really depends on what type of quantum dot you want to put in. As I said, if you can change the size of the quantum dot, you can make it at different colors. You can make it red, you can make it blue, you can make it yellow. It's just that if you make it red or even black, you can harvest all the sunlight, you can achieve the maximum efficiency. But sometimes it really depends on applications. For some applications, maybe people are not sensitive to the price. They are more care about the color for decoration purpose. In that case, maybe they make it red or green colors. with lower AC.
Thank you very much for this presentation, Dr. Wang.
Thank you.